Hi, everyone. My name is Jiajun Ma. It is my honor to present our work, the surprising effectiveness of skip tuning in diffusion sampling. And we are very fortunate to get accepted by ICML 2024. The motivation of our work comes from our in-depth analysis of the diffusion architecture. As we know, the most widely adopted architecture in diffusion model is the UNet architecture. UNet consists of three parts: the downsampling, upsampling, and the long skip connection that bridges the two components. However, we think the long skip connection will actually allow excessive noise during the sampling. Why is that? Let's consider a one-step sampling case. In that case, in the input side, that is the pure Gaussian noise, and in the right-hand side, that's your generated sample, right? As the noise enters through the downsampling part, the long skip connection will bridge or allow the noise to be concatted with the corresponding upsampling vectors without enough processing. So that part of noise will directly enter into the sample, and that's definitely not an ideal choice. So how to deal with such bottleneck? We propose skip tuning, which is very simple, but turns out to be quite effective design. We introduce a parameter rho that is times with the downsampling vector. The value of rho is restricted from 0 to 1, such that it will diminish the downsampling vector. And we also look into the details about the layer wise of the UNet. So in this figure, the x-axis corresponds to the layer from the bottom to the top. And the y-axis is actually the L2 norm proportion between the downsampling vector versus the upsampling vector. As we can see, there is a approximately monotone decreasing trend from the bottom to the top in terms of the proportion. And that motivates us to use a linear interpolation of the layer-wise rho value. In terms of the experiments, we firstly test skip tuning in EDM model. And as you can see, for EDM rho from 0.78 to 1, that means the rho starts from the bottom layer 0.78 to the top layer. That rho is linearly increased to 1. And we can see the FID get increased by nearly 100%. That is quite significant, and that such improvement persists if we increasing the sampling steps or changing different sampler methods. And we also test skip tuning in other diffusion model like latent space diffusion model or transformer-based diffusion model, and such improvement also persists. And we further test skip tuning in a more complicated stable diffusion tool in generating the high quality image. The left-hand side figure is the baseline figure generated by 20 sampling steps of stable diffusion tool. And the right-hand side is the our skip tuning with the same 20 sampling steps. As we can see, skip tuning successfully repair the image sketches the mouse, and we also test the human pictures, like the boy, as we can see, the T-shirt and the hand of the boy is kind of scattered. And then in the right-hand side, we can see the skip tuning successfully repair the image, and it's really in great quality. But given that such great successfulness, no matter in quantitative performance or the visual demonstration, we still want to ask, where does this benefit come from? What skip tuning actually have done so well? In our interpretation, let's first look at the score matching loss used in the training, the diffusion training. As we can see, it's basically the MSE loss between the fitted sample and the original sample. However, we think that might not capture the whole picture, as we can also measure the score matching loss in feature space, or we call the sample in terms of mapped by the discriminative models. And essentially, the discriminative model will map the generated sample or the original sample into the image embedding, and we will calculate the MSE loss in the embedding space. And we actually can see that the skip tuning will increase the loss in the pixel space. That is quite intuitive, right? Because your original model is trained in the with respect to the loss in the pixel space. So any changes to the original diffusion model should is supposed to increase the loss. However, the skip tuning can reduce the loss under diverse discriminative feature space. And we can see in this table, the baseline diffusion model and the skip tuning diffusion model. We can see the loss in the pixel space, the skip tuning actually increase that loss. However, for other loss in diverse feature space, including the Inception V3 or ResNet or even CLIP model, under all that remaining discriminating model, a skip tuning reduces the score matching loss. And we also extend our analysis or experiments by fine-tuning the parameter rho. However, it's kind of tricky, because if you directly fine-tune the rho, it may result in the FID explosion, because some accidental rho value that exceeds 1 will allow much more noise to pollute the image. So in order to solve that, we present a constraint by using the sigmoid function outside the rho, such that restrict the parameter within the 0 to 1. So in this case, the fine tune will work, and it get a very significant improvement over the baseline as well. And thank you for your listening.